and welcome to Algebra 2, Section 3.1, Evaluating Nth Roots and Using Rational Exponents. Let's start with some key vocabulary. In general, for an integer n greater than 1, if b to the nth power equals a, then b is an nth root of a. An nth root of a is written as nth root of a, like we have here, where n is the index of the radical. So what this is saying, if I have some number raised to the nth power and it equals a, if I need to find what the value of b, well, b is going to equal the nth root of a. Now, another way of writing this would be in exponential form. Nth root of a is the same as a raised to the 1/nth power. So we can write it in radical form, where we have n as the index, then we have a radical symbol, and then the big number underneath is called the radicand, would be equal to, in exponential form, a as the base and 1 over the index as the exponent. Let's find the indicated roots of a. Example A, we want to find the fifth root of negative 32. So we're asking ourselves, what could I multiply by itself 5 times to equal negative 32? Well, I know it has to be a negative number because a negative multiplied by itself an odd number of times will be negative. And I know it's going to have to be something small because I'm multiplying it 5 times. So let's try 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times a fifth 2 is 32. So the fifth root of negative 32 is negative 2. Let's look at example B. We want to find the sixth root of positive 1. Well, we want to think again, what can I multiply by itself 6 times to equal 1? And I know that 1 would work. But I also need to consider negative 1, because if I take negative 1 and raise it to the 6th power, it's still going to equal positive 1. So the sixth root of positive 1 is both positive 1 and negative 1. And we will see this anytime we have an even root of a positive number, we're going to end up with 2 values. Let's look at the key concept of the number of real nth roots of a if n is an integer greater than 1 and a is a real number. Well, let's start out with if n, the index, is an even integer. Well, if I take an even root of a negative number, we will get no real nth roots. For example, the square root of negative 4 would equal an imaginary number, not a real number, because nothing that can multiply by or square will end up being negative. The negatives will always cancel and end up positive. So we will have no real nth roots. Well, if a, the radicand, is 0, if I take the nth root of it, and if the nth root again is even, so it could be square root, 4th root, 6th root, etc. Let's just look at square root. Square root of 0 is just 0, because 0 to any power equals 0. So it wouldn't even matter if I had a 4th root, 6th root, 8th root, etc. It will always equal 0. Now you might notice that square roots, the 2 is implied. We usually don't show the 2 there, but the index for square root would be a 2. 4th root, the index would be a 4, 6th root would be a 6, etc. Now, if I take an even root of a positive number, so for example, the square root of positive 4, then we end up with 2 real nth roots. Now, if I just had positive 4, square root of positive 4 like that, usually we would just be talking about the positive 2. But if I was solving an equation and need to take the square root of both sides, I would need to put back in the positive and negative, because negative 2 times negative 2 still equals positive 4. And again, we can either write that in radical form as positive negative nth root of a, or in exponential form, positive negative a to the 1/nth power. Let's look at if n is an odd integer? Well, if n is an odd integer, like let's say cubed root, and let's say I take the cubed root of a negative value where a is less than 0, something like -8. Well, a negative times a negative times a negative is a negative, so I do get one solution, -2. So the solution is the nth root of a, or we could write it as a to the 1/n power, which in this example equals -2. So the cubed root of -8, or another way of writing it, -8 to the 1/3 power, equals -2, once again because -2 cubed equals -8. Now if a equals 0, and I take an odd root of it, like the cubed root, it's going to have one solution, and it's going to be 0. Again, because 0 to any power equals 0. Now if I take the cubed root of a positive value, like the cubed root of +8, we will end up with one real nth root, in this case 2, because 2 to the 3rd power equals 8. -2 would not work here because -2 to the 3rd power is -8, not +8. Without using a calculator, let's evaluate some numbers with rational exponents. Now, if you look at the first example, 125 to the 2/3 power, it's hard to calculate quickly in our head unless we first split it up. Now, what we could do is split up our rational exponent, this fraction, into two fractions. Now, you might remember when we write exponents, power to power, we end up multiplying. So, 2/3 is the same as 1/3 times 2. So, it helps if I think of this as 125 to the 1/3 power and then square it. 125 to the 1/3 power, well, that's the same as the cubed root of 125. Now, cubed root of 125, I want to think, what can I multiply by itself 3 times to get to 125? Well, 5 times 5 is 25, times another 5 is 125. So the cubed root of 125 is 5, and then if I square that, I get 25. Now, think about this next example. If I start out with a negative exponent, do you remember what to do with negative exponents? Yes, we need to move them to the denominator. If it's on the numerator, I can move the base and the exponent to the denominator, and it makes the exponent positive. Or if it started on the denominator, I could move the base and the exponent to the numerator to make the exponent positive. Now, once it's on the denominator, I'm going to leave it there, so make sure you carry the 1 over, and I'm going to split it up like I did in the previous example. I'm going to split up 4/3 into 1/3, and then the 4th power. And again, I can do this because 1/3 times 4, power to power, I'd multiply, and it is equivalent to 4/3. So again, I'm not changing the value, I'm just changing the format. Now notice I could first take 8 to the 4th power and then do the cubed root of it, but that's going larger than smaller. So it's much easier to first do the cubed root, make it go smaller before I take it to the 4th power. All right. Think through, what would be the cubed root of 8? What number could I multiply by itself 3 times to equal 8? Well, that's 2. 2 times 2 times 2 is 8. And then that needs to be raised to the 4th power. And 2 to the 4th power, 2 times 2 is 4, times another 2 is 8, times another 2 is 16. So, 8 to the negative 4/3 power equals 1/16. Now, I will expect that you can evaluate problems like these without using a calculator. But we also want to know how to efficiently use them on the calculator. So let's look at that next. Take out your calculator for these next 3 examples, and we're going to round our results to 2 decimal places. Now, 22 to the 1/4 power, that's something we could approximate the 4th root without a calculator, but it's not a whole number, so we can't find the exact value very easily. But on our calculators, we can go ahead and plug that in as 22, then push your exponent button. So for a lot of you on your calculator, it will look like that, but it could be y to the x power, It could be a box with another little box. And then put in the exponent. Now, if it keeps your exponent together as one fraction, you won't need parentheses. But some calculators you would need parentheses if you do raised to the 1 divided by 4th power. So you might want to try it both ways and make sure that you get 2.17, approximately, if you round it to the nearest hundredths place. Now, another way we could put that in our calculator is 22 to the 1/4 power is the same as the 4th root of 22. Now, it's not quite as easy to put on our calculator as a 4th root, so I would still probably use the exponent button and do it as 22 to the 1/4 power. But we could use the x root button, which you can find on your calculator sometimes near the square root button, or if you're using a graphing calculator, under the math button. For this, we would want to put the index number in first, so I'd want to put in 4. Then I would select the x root button, and then I'd put in the radicand, and we should get the same value of about 2.17. Go ahead and try example B. Pause the video if you need. 35 to the 5/6 power. Are you getting about 19.35? And let's look at example 3. Now, again, I could use the nth root button and do the 5th root of 11 and then raise it to the 4th power. Or probably easier and faster than that would be putting it as 11 to the 4/5 power. Would be the same thing. The 4 goes on the top, and then the 5th root, remember, is the same as a 1/5 power. And since 4 times 1/5 is 4/5, we can just do 11 to the 4/5 power. And on your calculator, you should get about 6.81. When solving equations with exponents, we still want to use inverse operations. So in example A, the first thing I want to do is isolate the x cubed. So I'm going to divide both sides by 6 in my first step. Then I end up with the x cubed equals 64. Then the inverse operation of cubing something is to take the cubed root of it. So if I take the cubed root of both sides, I get that x equals 4, because the cubed root of 64 is 4. Let's look at example B. Before I get rid of the -8, I do need to get rid of the 5th power. So how do I get rid of the 5th power? Well, I take the 5th root of both sides. So inverse operations to undo the equation, and always do the same thing to both sides. So I end up with x minus 8 equaling the 5th root of 100, which on my calculator I can put it in as 100 to the 1/5 power, or I could do the 5th root of 100. And I get about 2.512. And so at this point I'll change it to approximately. Now I don't want to round too far, or I want to round probably at least a 3rd decimal place if I'm doing this within the problem. If I can avoid rounding, that's usually the best. But I have one more step to do to solve for x. Add 8 to both sides. So I get that x is about 10.512. Now, as in with solving any equation, we can always check our answers by plugging back in. So in the original problem, if I put in the 10.512, subtract 8 from that, then raise it to the 5th power, I should get about 100. I get 100.02, which is pretty close considering I had to round in the process. So looks like my answer is correct. A lot of formulas involve powers, so this will be a common application of this concept. Let's look at one more example. An exercise ball is made from 7,854 square centimeters of material. Our goal is to find the diameter of the ball. We're going to use the formula for surface area, which is the surface area of a sphere is 4 pi r squared. And so I'll start out with plugging in what I know into the equation. So I know that's the surface area of the exercise ball. And I can solve this equation for r. Now, notice though, when I find r is the radius. So then think about what we'd have to do then to that to find the diameter. All right, and we'll come back to that. So first, let's look at solving for r. I want to get the r squared by itself first. Because this 4 is not squared, the pi is not squared, we need to get rid of this first. And we can do that by dividing by 4 pi. And on my calculator then, I want to put in the quantity of 7,854 divided by, and then I would need parentheses 4 pi, so that it will divide by both the 4 and the pi. And I get about 625. And so to solve for r, I need to get rid of the squared. Inverse operation, take the square root of both sides. Square root of 625 is 25. So the radius is about 25 centimeters. And to answer the question asking us to find the diameter, well, the diameter is twice the radius, so I need to multiply that by 2. And so the diameter is about 50 centimeters. And that concludes our lesson 3.1, evaluating nth roots and using rational exponents. Thank you.